we'll move on to the next topic, that is multiple access. So let's look at the requirement of multiple access first, right? Let us consider a scenario wherein you have a specific requirement that from one location you are sending multiple signals, okay, to maybe different locations, right? Let us say we have let's consider example of a satellite where we have the multiple access technique is being used very widely in the communication. That's one such application is the satellite communication. Okay, so in case of say a satellite transponder, right? Satellite transponder is the one where the conventional microwave line of sight uh, repeaters are they are not being used, right? Because it's not simply line of sight, right? Because you are not sending message from one point to the other point. That's what we do in a line of sight microwave repeaters. Okay, but when it comes to the satellite transponder, let's say we have many stations on Earth, right? And they want to access the satellite from widely different locations on the Earth at the same time. Okay, simultaneously, you want to access the messages coming from satellite transponder, right? So there could be thousands of stations over Earth to access a given transponder on a satellite at a given point of time simultaneously, right? But the idea is that maybe the message which each station has to receive is different. Okay, it's not same, but the messages are all the messages see, it's like you cannot keep sending different messages over different channels. That's actually a very difficult job. So every messages will be put up over a specific maybe frequency or time or something similar to that, and it will be sent over to Earth, towards Earth from the satellite transponder, and each of the station will pick up the corresponding signals only, like the channel, right? For example, if we consider one application of the satellite communication is our the TV set-top box, right? So you will pick up only the channel which you want to see by some technique, right? So every signal, the signals corresponding to each and every channel you have access to will come to your dish antenna, through which it will come to the receiver simultaneously. But only that channel which I want to see, I can pick up, right? I can select that, right? So you see that that's actually the concept of multiple access, because my neighbor might also receive the similar signals, but he or she is going to watch a different channel, right? So see, multiple access, multiple people can access the same transponder of a satellite simultaneously, but the messages received could be different. Okay, you have an option to select what you want. So this whole idea is called as the multiple access. All right, so this whole concept, the capability of doing such a communication, is called as multiple access, right? So what we can say about multiple access, the idea of multiple access uh, is to permit the communication resources resources to be shared by large number of uses. So this is the idea. Okay. Another application again that comes under the satellite communication is the telephonic call, which goes through the satellites. Right. Whenever we want to talk uh, to the relatives which are okay, they are, if they are present over a different continent, right? So we don't prefer going through the regular wired communication channel. It will be a wireless channel. So one of the option is to use of the microwave. Again, microwave communication is used something like within the country or neighboring countries only. But when you want to go beyond that, like India to Europe or India to US, etc., it's always the preferred technique is to go through the satellite, right? So there will be a base station which sends the message to the satellite. Satellite will send that message to another base station or receiving station located at that continent. So directly, right, without any other peer points, right, we can have a communication. So that's again here also you can see in such examples the users are actually using the satellites to communicate between each other. That's also another application, right? Instead of single something like this, there is one satellite, single satellite sending to many, right, points. This is one application over a geographical area you are trying to communicate. The other application I told was there is, let's say, there is another satellite over here, and users are sending the signals from one location to other location, right, like this. So you see three signals are going in, three signals are going out, like this. This is also multiple access. Multiple people are trying to access, many people try to access the resources of that satellite, right, so that they can communicate with each other. So this is also another application, right? Many application can applications can be built like this, but this is the general idea. Okay. All right. So when we say uh, we are going to share the resources of the communication system, it is desirable that sharing of the resources will be accomplished without causing any serious interference with each other. This is actually important, right? Whenever we use, it's something like whenever we use multiple communications happening simultaneously within a small region, right? Definitely, we observe a lot of interference. Like there is a mobile communication happening. I'm talking over mobile. Simultaneously, somebody is listening to radio and television. Like you see the interference. So in such a small region itself, we see interference. Then this is much larger application, right? So there will be interference. So how to avoid that? So that is the second part of the multiple access technique. So first thing is to provide a good communication, right? Uh, for multiple, like sharing a resource with multiple users simultaneously. Second thing is you want to make sure that without you don't cause any serious interference to each other. So uh, this has to be accomplished without causing serious interference to each other. Okay, so this is the very rough idea about the multiple access techniques. So basically, we have four types, four different techniques using which we can achieve the multiple access. All right. So the first technique is called as the FDMA, or the frequency division. So it is frequency division, multiple access, and short form for this is FDMA. Right. So as the name suggests, you are trying to use the frequency as the parameter for accessing the resource, right? So we try to use disjoint sub-bands of frequencies, right? Disjoint sets, we are very familiar that there is nothing common between any of the sets in disjoint sets. Similarly, disjoint frequencies are used. They are not, you are not going to allocate the complete frequency for a user, right? But a band of frequency, which is something like a sub-band, right? Not the whole band, right? So disjoint subbands of frequencies are allocated to different users, to different users on a continuous time basis. So here, as uh, we can see here, first thing is disjoint subbands of frequencies are allocated. So that takes care of what is called as the division of the frequency, right? You divide the frequencies into subbands, and each of the band is allocated for a user. Okay, and within that band, again, you can use you can make multiple users to use the subband. But as of now, let's not go to that level. Let's say that okay, you divide the whole available frequencies into subbands. Okay, each of the band could be of maybe 100 hertz, 1000 hertz, 1 megahertz, or any type. Okay, so you divide, and that each of the band you sub band you created is going to get allocated to different users, right? So continuously you allocate it, right, to that user until and unless the user wants to stop communicating, right? So all the time the subband is with that particular user as far as the user wants to communicate, right? So now let us say, okay, communication will happen, each user will use their own subband, right? So whenever it comes to the uh, frequency based communication, right, there will be interference because of some non-linearity in the channel, or on the source side, if your frequencies are not integer multiples of each other, then right, you will see they are not orthogonal, so definitely the concepts of interference comes into picture, right? So just to avoid that, to reduce the interference between the users, allocated adjoint or adjacent what you call channels, right? Like, so present channel and the next channel, right? We try to introduce what is called as a guard band. It's like it's going to act like a buffer zone, right? And in the buffer zone, communication is not allowed. All right. So when we say we achieved such a communication, so the second question comes: what type of interference you are going to get and how you are going to avoid? So to answer that question, we'll write this point. So to reduce uh, the interference between the users allocated the users allocated the adjacent channel bands. We use what is called as the guard bands used. So these guard bands basically act like a buffer zone. Okay, in buffer zone, you cannot communicate. So let's look at a diagram representing this kind of communication. How the time versus frequency, right, can be plotted for such a communication. So this is the time axis, and let's say this is the frequency axis, right? So throughout the time, frequency gets divided, right, among the users. So let's denote the frequency in this fashion. Let me assume that I have say three communication channels at a given point of time, right? I divide my whole available frequency into say three parts possibly, and I need to introduce the sub bands or the guard bands as well. Okay, so first let's divide this into three parts. Right, there will be gap. Yeah, minimum gap. True, 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 true. Right, right, exactly, exactly. So that is like the buffer zone that exists between the channels. Okay. Now let us say we have the vertical axis is frequency. As I move up, right, I am changing the frequency. So the bottommost one could be the frequency band number one. All right. So maybe this is say few megahertz, like 0 to 2.5. Then the next one will start after a buffer zone of zero point 0.5, right? It maybe it is starting from 3 megahertz to next this thing. Okay, I'll write the frequency values later. So let's write the frequency bands first. So this is frequency band number 2, right? And we have frequency, this is band number 3. So in the middle, I have what is called as the buffer zone or the guard band. This is the guard band. Again, I have another guard band like this. So you see, throughout the communication channel, the user 1 can use this, right? User 2 can use the frequency band number 2, and user 3 can use the frequency band number 3, and so on. So how many users you have, so many frequency bands you create, right, within the allocated band of communication. All right, so let's write some values now. So it may be the first band, every band is say 2.5 megahertz, let's say. So this is 2.5, then it starts from 3 plus 2.5, so that should be 5.5. So 3 to 5.5 megahertz is allocated for user 2. Then again I add a buffer zone of zero point 0.5, so this makes 6.0. 6.0 plus 2.5, this is 8.5. Correct? So you see, frequencies are getting divided among the users, right, simultaneously for during the fixed amount of time. Time is fixed, like you can use any at any point of time. So somebody might communicate at 2 seconds, right? So user 2 may use at 6 seconds, user 3 may use at a different time, or simultaneously. When somebody is using their own frequency band at 2 seconds, somebody else can also use their band at the same time, So there is no restriction. So since the frequencies are completely different over here, like the communication frequencies are different, right? There will be no interference or less interference. So how they can use, it's left to them. They can use a frequency modulated wave to transmit, right? Within this band, somebody might use the amplitude, right? Modulated wave. Or in digital, they can use ASK, PSK, FSK, right? So it's left to them what they want to use. But the frequency should be within this band. That's all. Allocated band should be used. Done. All right. Let's move on. Now, again, we'll come to the second usage of the guard band, right? The first usage is that it simply tries to avoid the interference between the channels. Again, now let us say we want to say that user one wants to communicate with the right somebody else on other side, right? Maybe it's a telephonic conversation, right? On, you see, this whole thing will be a channel, right? All the three bands together will be sent as a channel to a satellite. Satellite will pick up whole thing, and right. So in the sense, this data and this data should not reach the intended person, right? Only this message should reach, right? So the idea is that on the other side, you will use filters to pick up only 0 to 2.5 megahertz. Let's assume. Maybe in this case, it is a low pass filter, but if it is user 2, it has to be a band pass filter. Okay, between 3 to 3 to 5.5. But you see, ideally speaking, we can say we can create a filter that picks up exactly 3 to 5.5 megahertz, right? So whenever our intention is that you have to pick up only the message which is intended to you in terms of frequency, right? We use the filters. Okay. Okay, I'll write the filter now. So let's just see. Again, I'll compare both ideal and the practical filter. Right. So if my intention is to, for user one, I just want to create a filter like this. Fine. This is my requirement. My requirement is this is 0, this is 2.5. But is it possible, right? This is some h of f versus f, frequency versus this, right? So my question is it possible? Right? So the answer is no. It's impossible to create such a filter, right? Because sharp cutoff is impossible, right? We have seen in digital signal processing, whether you use FIR, or any higher order filters, still you don't get a vertical, right? The sharp cutoff like this. So what you can get is something like this, right? So when I say something like this, you see you are actually moving out of your band, which indicates that you will definitely pick up something outside your band. Okay, so one option is this, right? So in this case, you see there should not be any communication outside 2.5 until some frequencies, right? Which, that's why the guard band is used. You see, you will make a filter, the filter's response will enter into this region, correct? So you see, this is 0, this is 2.5, I slightly move outside, right? That's what is happening now. So the guard band is not just used to avoid interference, it's also supporting you to build a filter of certain capability, right, which actually gets extended slightly to the buffer zone or the guard band. This is one option. Definitely you have another option saying that why don't you design a filter that actually works like this and limits within your 2.5, right? Because you can say that question, but it's actually you are losing your message. What if the user sends something very close to 2.5? Actually, if you design a filter which is shown in the red colored, right, marking, then you are losing that data, right? You lose that data. So it's not suggested to design such filter. You completely cover your region and then get extended, right? Then you extend it into the buffer zone. True, true, true. So now because of uh, uh, this kind of response of a filter, you can say that there is we are trying to introduce little bit of interference, right? But we'll make sure that you don't, if you make sure that you are not communicating in the guard band, you will never send a message. But on the receiver side, because of the restrictions of the filter, we are trying to uh, slightly extend our reception band into the guard band. Okay, but if there is no communication that is happening in the guard band, then no issue, you will pick up nothing. Okay, so this is how the guard band is used. So let me write that point. Okay, uh, these guard bands are necessary because of the impossibility of achieving ideal filtering. Okay, then in this kind of communication, uh, recognizing that non-linearity of the device which you are going to share, right? Our idea was to share the resource, right? For example, satellite. Now the satellite transponder is actually a non-linear device. Okay, so because obviously, so we may say that how it is non-linear, right? Why not it is linear? You see, what are the components used, right? You use FETs, right? You use olden days BJTs. Before that, traveling wave tubes were used inside them. Okay, in the manufacturing process, because it's a communication device, and you definitely use semiconductors, right? We have seen, starting from diode, it is a non-linear device. So the input given to the device and the output of that device, right? There is a non-linear relationship. So look at the diode current equation. It is e to the power exponentially rises with the input voltage. So obviously it is non-linear, correct? So look at the input output characteristics of a BJT, FET, right? Anything you consider, right? They are non-linear. So that's why the idea is that these devices are non-linear in nature. So the next point is, what is the main reason of interference, right? So in this technique, that is FDMA, right? Uh, Recognizing that the non-linearity of the device or of the resource which you want to share, right, is itself is a primary cause of interference between the users, right? So this is something like, since you are using many of such semiconductor devices over there during your communication, actually there is a lot of non-linearity, and we have seen in the basics of BJT, FET, those chapters, right? We have seen that, right, whenever multiple devices operate at neighboring frequencies, those devices will cause interference to each other. So that's the reason of interference over here, right? So let's just write one point about that. So this is the recognizing that the non-linearity of the resource being shared, in bracket I write satellite, Okay, right. So that's the resource being shared, right? So satellite is our example. That's why I'm writing satellite uh, is the primary cause of interference, right, between users. Now, so because of this, again, I'm coming back to the example. Say, let's say we are using the idea of satellite communication, and you are allowing multiple users to communicate, maybe for a call or the reception of channels, the TV channels, etc. Now, because of this reason, right, that is, whenever I use a particular BJT or FET inside that satellite transponder, it causes interference to the neighboring channel, obviously, by actually you can see the output current equation, which is actually a nonlinear equation, right? There is, if I have a cos omega t as input, it generates cos omega t, cos square omega t, cos cube omega t, and cos to the 4, which actually in terms they are the integer multiples or harmonics of your cos omega t, correct? Because cos square theta is 1 plus cos 2 theta. So if I have cos theta over there, cos 2 theta comes at the output, cos 3 theta, 4 theta, etc. will definitely come in the output. It's actually causing the problem, right? So that's the problem. I identified that now. So what do you do? How do you reduce this? So you are going to make sure that the amplifiers or any other sort of circuits, maybe filters, uh, within that shared resource is going to you are going to make sure that it's being operated below its complete capacity. You are not going to use it to the full extent, right? Whenever, so you see, you don't give the full voltage as input, you try to give a lesser voltage, so that at least, right, you reduce some interference, okay, because of that device. So between the users, I can write the are operated resources are operated below their capacities. In the sense, maybe you make it to operate at a lower voltage, you make sure that lesser current flows over there, and also you will make sure that you are trying to possibly uh, give less power. Okay, so these are the options what you can do to reduce the ultimate interference between the users. So what happens as a consequence? The power efficiency of our FDMA technique will be reduced. Okay, so this is the major problem. So now we are talking about the problems associated with the FDMA technique. So it's obvious that the power efficiency of any FDMA technique gets reduced, right? So this is called as, there is a specific name or technical term for this. It's called as the power back off. So this is the major issue with the FDMA technique. So far we discussed about the FDMA, what exactly it means, right? And we saw uh, some of the features, right? Like guard bands, right? What's the use of guard bands, etc. And also we have considered one issue related to the FDMA technique. Okay, right. Then we'll move on to the next technique. This is The second multiple access technique, we call it as time division multiple access. So you divide time as the name suggests. Short form is TDMA. All right. So in this case, we cannot divide the frequency. In the sense, each user will not get a part of the frequency, but user gets complete frequency. Complete band is allocated to a user, right? But if you do so for the complete time, then other users cannot communicate, right? So what you do, you give the full band of frequency, right? But give it for a very short duration in time called as a time slot, right? So this is the idea. I'll write. So each user is allocated the full spectrum occupancy of the resource, but only for a short duration of time called, and there is a name for this, uh, it's called as time slot. So now what we do, we'll look at the diagram first. Okay, let's check how this is going to look like. Okay, now this is the time axis and this is the frequency axis. Right. So here our idea is that complete band of frequency gets allocated to the user, but for a short duration. In the sense, time is going to be divided. Time gets divided. Frequency is complete access. Like the previous case, time was complete, right? You had complete access over time, but you have, right, you had a restriction over frequencies over there. Now no restriction over frequency, complete frequency is available for a user, but for a short duration of time. So what we do, we divide this in terms of time. So you see the division happens in time. So this is a time slot. Correct, correct, correct. So this is a time slot number one, and maybe I'll divide this like this. And again, just to avoid the timing errors, we'll introduce the concept of guard bands. But this actually is a time slot. Okay, you introduce the bands like this, guard bands, right? Again, right. So now you see this particular yeah, we can write like this. Correct, correct. So this is time slot number one, time slot number two, time slot number three. Then we have the guard bands. Okay, so I'll change the color. So I'll write guard bands. One is this, and one is this. So time is getting divided. That's our first observation, right? User one can send the message during this time at any possible frequency, right? Starting from 0 to maybe the highest one was 8 megahertz, I guess, previously used. So within this 0 to 8, you can use any modulation technique, anything you want, right? Any frequency, anything, right? But you have to be, there is a restriction for you to use that particular channel in terms of the time. Like if it is allocated time is 2 milliseconds, you have to stop within 2 milliseconds. As we know, the time has been divided into the slots, and depending upon the number of users, right, you may get several slots or only one slot within a given time period. Okay, so this is how it's going to work. Let's say each slot is in milliseconds possible, right? So the division happens like this. So there is or let's say in seconds, this is more easier. So every user gets a 2.5 seconds of time, and there is a zero point 0.5 second of guard band. So this is 3, then plus 2.5 is 5.5 seconds for user 2 in time slot 2. Again there is a buffer of zero point 0.5 to make it 6, then 2.5, that is 8.5, and so on. This actually continues, right? If only 3 users are there, right, then the time slot 4 we write after this will be allocated again for user 1, right? So uh, they get a chance to send their message in a circular fashion. User 1, user 2, user 3, then once again user 1, user 2, user 3, as the time progresses. Okay, I'll write about the buffer zone now. So the buffer zones in the form of guard, we can call it as guard time, okay, or we can call times because there are multiple such slots. Guard times are inserted between the assigned time slots. Okay, now uh, because of these buffer zones introduced between the time slots in the form of much smaller time slots, you try to avoid the uncertainty of timing. Maybe it is in terms of sampling or any other timing errors, right? We can try to reduce that straightforward. Okay, so let's write that uh, this reduces the interference between users by allowing for time uncertainty uh, due to, there could be many reasons. We'll club all of them together under one category called systems in imperfection, right? There will be many errors, right, in terms of time that might arise. We'll call it as system interference, imperfection, sorry. Okay, so that said uncertainty due to uh, system system imperfections, right? So this actually includes the timing errors due to uh, timing in terms of clock, because multiple, you have many devices over here, right, trying to work simultaneously. So there will be difference in terms of their clocking frequencies, right? Maybe they are different, because of which one tries to sample at a point of time, other one is actually not sampling at that moment, right? You have some uh, mismatch in terms of timing. So this comes under, actually, if we want to put the right words here, it should be synchronization in terms of the synchronization schemes of each device. Okay, so you because of so many users using the technique, right, using the communication channel, right, you cannot use a common, what you call, common clock for everyone. That's impossible in this case. If it is like a computer, single computer, right, then definitely you may use many devices to many IO devices and memory and its own hardwares, like that. You can definitely use a single clock over there, right? You can right. Correct. Yes, right. So because of that restriction, where uh, wide variety of users using the channel at different from different locations, you cannot make use of common clock. So there will be a synchronization issue. So because of which you have to allocate the guard band, which takes care of this. All right. All right. But we have an advantage over here, right? The advantage of something like TDMA over FDMA is that the resource which you are trying to share, right, will be able to operate close to its full power efficiency, right? It's full power efficiency, because the frequency is not going to cause any problem with the neighboring time slot, because within the time slot you can use the full power you can use, because each user gets complete spectrum within that time slot. So you can use any frequencies or multiple frequencies, anything you want, right? So there is no restriction, right? uh, Here the advantage is that the resource uh, can be operated at its full spectral efficiency, right? So in other words, if you are talking about the FETs or BJTs, you can make them to operate in the saturation region where highest power, right, gets used for a given device. Okay, so in TDMA, which region you prefer to operate any device, it's a saturation region. In other case, you may have to go for active or, right, turn on and off in between, like that. You have to save some power over there, but that restriction is not there in TDMA, which acts like an advantage of TDMA over FDMA.